Hi, good morning and welcome to this new session on n-step temporal difference. In the last session we have seen what is temporal difference control and also TD0. It's a one-step temporal difference operation. Now we are going to discuss the n-step temporal difference, and also in the coming sessions we will discuss more methods based on temporal difference. First one is TD lambda, temporal difference lambda. Then we naturally move on to salsa lambda and Q lambda, both off learning and on learning policies. Okay, in this session we will discuss TDN or n step temporal difference as an extension of TD0, one step temporal difference. Then we also formulate the mathematical frameworks for n step transition. So first of all, discuss the concept of n-step TD as a transition from ordinary TD to a more updated version. Our ordinary TD is TD0. That means we simply update the existing state value by the bootstrapping single step forward. So this update of one-step TD methods is based on just the one-step reward bootstrapping from the value of the state one step later as a proxy for the remaining rewards. That means to just calculate existing state value using its immediate return, that is a reward, and the bootstrapped return at the next state, next later state, that is usually denoted by v of s dash or vt plus 1. Okay, the n step temporal difference will uses an update based on an intermediate number of rewards. That is very important, an intermediate number of rewards. Instead of one step reward, it take intermediate number of rewards, rt plus 1, rt plus 2, etc. Okay, more than one but less than all of them until termination. It should be definitely more than one. If it is one step, it is automatically TD0. It is more than one and less than, naturally less than the end number of the end state. If the end state is at t, then we take up to st minus 1. That is the idea. In short, methods in which the temporal difference extends over n steps are called n step TD methods. It's a very simple idea. TD0 is one step. N step TD means n step reward accumulation. We consider n later steps and its rewards to calculate or update existing state value. That is the idea of n step transition or n step TD. This is simply a transition from our ordinary temporal difference method to a higher level to make use of rewards up to next n later rewards. Okay, so the mathematical formulation is so straightforward. It is denoted by a suffix notation gt full colon t plus 1. That means t plus n minus t. gt to tn plus n is equal to rt plus 1. That means immediate reward at state t plus next state reward by a discount factor gamma. So gamma into rt plus 2 plus etc. plus r gamma raised to n minus 1 rt plus n plus gamma raised to n vt plus n minus 1 st plus n. That means it is a sum of later rewards by a discounting factor, because reward at state n is discounted with a factor gamma raised to n minus 1. We have already discussed what is the meaning of discounted factor. The discounted rate is actually something like present value of money in finance. If we invest 100 rupees today, after 10 years the value for that 100 rupees is approximately 10 rupees. So the 100 rupees in 2020 become 10 rupee in 2040. That 10 is actually the present value corresponding to 100. Now we are put it in our savings bank. That's all. So gt t plus n, we can think of t plus n minus t, that is n. This is n step target return. Okay, now we think about value updation. Instead of that gt, I am using gt t plus n. That is the only difference between our original TD0 and this n-step TD. The natural state value learning algorithm for using n-step return is defined as Vt plus n st. Vt plus n st is equal to Vt plus n minus 1, just previous state value, plus alpha into, this alpha is the learning rate. Instead of that st plus 1 in our TD0, it changes to this n-step return, that is gt full colon t plus n, gt t plus n minus current state value. That's all. This gt t plus n is actually rt plus 1 plus gamma into rt plus 2, etc. In the case of TD0, this gt t plus 1, that is equal to rt plus 1 plus gamma into the next state value, that is v of st plus 1, like that. This is the difference. Since it is a n-step temporal difference with a terminal state at st, the small t can varies from 0 to capital T. So just replace our one-step bootstrapping by an n-step cumulative sum of returns. That's all. Now we can compare this n-step TD and Monte Carlo method. Under what condition this n-step TD becomes a Monte Carlo? See, in the initial case we take only one step transition. That means value updation is happened only single step. So this is one step TD or TD0. When I use two state values, two rewards and corresponding state values, it becomes two step TD. This is the present step, first step, second step, two step TD. Now what about three step TD? This is my existing state. I have to take rewards for the next three states and the corresponding state values. So first state, second one, third state. Okay, three step TD. If it goes on n steps, that means the current state value is updated with the help of later n step rewards. It becomes n step TD like this. Note that it is not the end state, the terminal state. Now it is goes on continuing. Then what happened? This n changes to infinity. So it will automatically come to the terminal state, that is written by this shaded square. So it starts from an initial state, then goes on all the states in an episode and end at a terminal state. This is called our Monte Carlo. So the TD0 is changed to a Monte Carlo with these increases of n. If n increases gradually, this one step transition changes to n step transition, and it continues increasing, it automatically goes to Monte Carlo. So TD, n step TD extend TD0 to Monte Carlo. So this n step TD can help us to develop Monte Carlo from a temporal difference learning. Okay, so Monte Carlo is just a special case, a particular case of this TD. N-step TD can be extended to Monte Carlo. Next is an error reduction property. This property is a statistical property that helps us to assert that this type of accumulated return doesn't make any problem. It will never affect the convergence of this return in any way. For that, we make use of this inequality. Maximum of all states, expectation under the given policy, GTT plus n, given the starting state is yes, minus v pi of s. I am starting with the state yes, then I calculate two values. One is the actual value, state value, the state yes with respect to the given policy. Another one is expected. Expected means average value of this return, n step return, GTT plus n. This difference, expected value minus actual value, expected value minus actual value, this is actually temporal difference. Its maximum is always less than or equal to gamma raised to n into maximum over all s Vt plus n minus 1s minus v pi of s. That means this Vt plus n minus 1s is actually the updated value using n step TD. This updated value minus actual value, and its maximum is always greater than this particular value. That means this updation is always, this error due to this updation is always less than or equal to this discounted error. So this n step cumulative return doesn't affect the convergence of our TD algorithm. That is the essence of this inequality. because of the error reduction property, because of this property, one can show formally that all n-step TD methods converges to the correct predictions under appropriate technical conditions. See, this is our current prediction. Instead of this current prediction, if I am using this n-step return, its maximum error is always less than this current error. So this update never incur no more error in our prediction. So it is better than the existing operation. So this is an averaging operation. So hence we can say that this TD is a family of operations. TD is a family of methods. What methods? Our reinforcement method. What it is? TD0 first. That means TD0 is the initial one step transition or one step update to the state value. Then TD1, TD2, etc. At last, when n tends to infinity, that becomes MC. So TD, the temporal difference learning, create a family of learning algorithms starting from TD0 and ending at MC. We will see this property more advanced versions in next classes. Okay, this is the pseudocode for n-step temporal difference by Sutton. So very simple. We start with an initial policy. You have to set the parameters. For example, learning rate, it always lies between 0 and 1. C is open, close interval. Then initialize V of S arbitrarily. You can use random numbers or 0. That is your choice. Then all stores and access operations for ST and RT. ST is ordered by STRT. For any ST, the corresponding return is RT. Can take their index mod n plus 1. That means this index mod n plus 1 means whatever be the position of the state, you have to retain the value after the n step as the initial step. That means when I take the modulo operation n plus 1, n plus 2 mod n plus 1 becomes 1. N plus 3 mod n plus 1 becomes 2. That's all. After this n plus 1 state, all states has the same values as S0, S1, S2, etc. That means after n plus 1 state, there is no new states. We fix that. In order to ensure that it is just an n-step TD. If you apply n-step TD from one position to another position, that n-step will taken. Then the consecutive steps will be considered as the initial state. That's all. Loop for each episode. Initialize and store S0 not equal to terminal. If we start with an initial state S0, if it is not terminal, then we do this. If it is a terminal state, there is no need of update because its value is always 0. Then I choose t is equal to infinity. That means the last state or the terminal state is infinity. That means there are infinitely many states are available here. Then loops over t is equal to 0, 1, 2, etc. starting from S0, S1, etc. Then if t less than t, that means the current t value is less than infinity, then you should take this action. That means you just calculate n step return and use make updates. It's very simple. Take an action to pi of st. We start from the initial state to next state using an action, arbitrary action A. Observe this and store the next reward. We have to store the reward in an intermediate temporary variable. Then only we can sum up all these n return into our gt full colon t plus n. So r t plus 1 is stored there, and next state as st plus 1. We have to move from the state st to st plus n. Then only we can collect all the return. That's all. If st plus 1 is terminal, then t is equal to t plus 1, because if the terminal state, the remaining states will become same as the initial steps. As in this this modulo operation, we fix this t as t plus 1. Then if I create a temporary variable tau is equal to t minus n plus 1, because it gives the time steps. At what time steps I am going to take the updates. So it is written here, tau is the time whose states estimate is being updated. At which state I am going to put update, because there are many variables running over. One is from initial state to nth state to calculate the return. Another one is to calculate the correct state time step in which we are going to update the state values. Then if tau greater than or equal to 0, that means the time steps. It is a positive time steps. You have to update it using our formula gt. G is equal to sigma over I is equal to tau plus 1. That means next you have to update the current state value or current return using the next n return, n consecutive return. That is why I varies from tau plus 1 to minimum of tau plus n comma t, because we have to ensure that there are n steps. Then gamma raised to I minus gamma tau minus 1 ri, sum of returns by the discounted factor. Then if tau plus n less than t, then g is updated with this g plus gamma raised to n v of s tau plus n. This n step updates iteratively. If v of st is equal to v of st plus alpha into the return g, n step return g minus v of s tau, then until t is equal to t minus 1, because we start from 0, the terminal state is at capital T, so the last non-terminal state is t minus 1. The corresponding time steps is equal to t minus 1. So we repeat this over over all t values from 0 to etc. up to this any state. It creates n step temporal difference update given by vs tau is equal to vs tau plus alpha into g minus v of s. So remember, our previous formula in mathematical derivation is a closed form equation that just represent the complete value update rule, but in computer we are doing it in a iterative way. We update it iteratively because it reduces the number of variables and also it reduces the computation complexity that we have already discussed in our stochastic gradient descent, etc. So thank you. In next section we will make use of this n step TD and develop a new TD algorithm named as TD lambda. Our aim is to generate a unified model that will move from TD0 to Monte Carlo. One option is n step. Next state we will see it creates a new special type of algorithm that make use of all good qualities of statistics, and it actually create a distribution. The distribution will ensure a good convergence in updates. That is the idea. Thanks to Richard A. Sutton, the originator of this reinforcement learning, to this level, because all these contributions are from his hand. From his head he create this idea of TD lambda and further off learning and on learning policies in reinforcement learning. We will see that in the next lesson. Thank you very much.